So this is the last lecture before the exam on vapor power cycles. We've covered a lot of territory. We've covered the Carnot vapor power cycle, fair game for the exam. We've covered the Rankine, the ideal Rankine vapor power cycle, fair game. We've talked about enhancements by having superheat, reheat. We've talked about regenerative vapor power cycle with open and closed feedwater heaters. And even the homework that you did today had efficiencies, isentropic efficiencies for the pumps or for the turbines. All of that is fair game, and I'll have a couple other topics today. Let's press forward. Last time we talked about deriving the equation for this Y2 that is diverted down to feed the open feedwater heater. How do we do that? Let me do it. Let me get your attention first. Are you ready to continue? All right. Do we want to spend time on this to get Y2? Yes or no? Yes. I got a couple no's. I got a couple yeses. Let's do a show of hand. Yes. Show of hand. No. All right. Let's go ahead. Thank you for participating, but just like in any election, 50% or less or more is not happy with the results. All right. So to calculate, I'm going to call this Y2. I know that double subscript what the book uses, but it's a little awkward for me. Okay, now, what we have to do is we have to isolate the component, and we have to do both a mass balance and an energy balance. So if I isolate that component, I'll have coming down a Y2. What do you mean by coming down Y2? Well, if you wanted to, we could do it by the mass flow rate that feeds the open feed water heater, and then we'll write a mass balance equation. Then we'll find out that, if you divide the whole equation by m dot T1, what goes through the first turbine, then you'll get it in terms of fractions. So this would be Y2 coming down, coming through this first pump, out of the condenser, through the third turbine, through the second reheat, coming from this way. That's all 1 minus Y1 minus Y2 as a fraction, isn't it? So this is 1 minus Y1 minus Y2 coming from, and it's coming from state 8. This is coming from state 4. All right, let's go here. What is this one? This is state 13. And what's that? Well, it's what went through the trap. That's what went through typically the shell side of that closed feedwater heater, and that's what was diverted down to the shell side of the feedwater heater. So that is Y1. Is it not? And then what goes out? Well, you just do the balance, and what goes out goes through the second pump, goes through the tube side, goes through, that's back to 100%. So that's state 9 at 100%. The book sometimes uses this percent in parentheses like that fraction or percent in parentheses to indicate what fraction that went through the first turbine is coming in each of those inlet streams. Does that notation make sense? So really the mass balance is all described by these terms right here. So let's do the energy balance. So we have enthalpy at 4 bringing with it, or coming at a rate of Y2. We have coming in enthalpy of 8 bringing with it 1 minus Y1 minus Y2. And we have H13 bringing with it Y1. And the only out, so we'll put it on the other side instead of a negative. We'll just put it on the other side. It'll be H9 times 1, 100%. It looks a little abstract, but I think I've done enough of these to be readable to you. Is that readable as an energy balance? Then the game is up. The game is over. It's just algebra at this point. So we want to get and isolate Y2 in terms of everything else. Throw everything else on the other side. So maybe I should do it in 2 steps. What I'll pick up is I'll pick up H4 minus H8 times Y2, and then throwing everything on the other side, I have H9, and then I'll have, let's do this one, minus H13Y1 minus H8 times 1 minus Y1. You can manipulate it a little differently, but this will work. Make sense? And so what I would be looking for is Y2 is equal to, and then if you want, you could put a H9 minus H8. This doesn't matter how you express it. It just has to be correct. Plus H8 minus H13 times Y1 divided by H4 minus H8. I'm going to pause. I want you to look at it. And if you don't find an algebraic or another error in this, and if you agree, then you give me your thumbs up. I have 1 thumbs up. I have 2, 3. All right, so there you go. These problems get very long. And I've tried to keep them short up to this point, but there's just no shortness in some of these problems. And a lot of times they can throw you, and I know that homework that you had to do today gave you the problem of, oh, consider the isentropic efficiency for this turbine or that turbine. Consider the isentropic efficiency of this pump or that pump. True? So I've reworked this problem now with 3 turbines. Each of those turbines have different isentropic efficiency. 2 pumps, each of them have unique, different isentropic efficiencies. It just makes the problem super long. But I have confidence you can work a problem as long as this, if not longer, in 50 minutes from scratch. That's a joke. I'm glad you laughed. Otherwise, people start throwing things. So, you need to have worked problems like this in homework. You must have. It's required. I mean, it's expected. They were assigned. And so you know what it feels like to work a long problem like this. So what is going to happen on the exam, Professor? Well, typically what you do is you give most of the solution to a long problem, and you withhold some parts of the solution, and then you ask them to fill in the blanks. So you might anticipate that. Okay? If you know what you're doing, somebody says, can you please tell me the pressure at state 13? If I know the pressure at 4, and I know the pressure at 8, and I know the pressure at 9, or some of those combination, I can get 13, can I not? Somebody says, tell me the temperature at 8. That's a little tricky. It's going to be slightly above the temperature at 7. Now, to do it to 3 significant digits is going to be really, really hard. But does somebody know how they would actually do it, to try to do it using the data in the tables to 3 significant digits? This is a hard question. How would you do it? It wouldn't be very accurate. I tell you, you'll get a number to 3 significant digits, but I'm telling you it's not accurate using the data available in the tables. Yes, you're going to use the work of the pump as VDP, so you'll be able to calculate that work of the pump. You know with confidence the enthalpy at 7, true? That's the enthalpy of saturated liquid coming out of that condenser. And now you're going to get the enthalpy at 8 as the enthalpy at 7 plus the work of the pump. And if there's isentropic efficiency, you divide by the isentropic efficiency. It makes a little bit larger work of the pump, true? But what did I ask? Get the temperature at 8 or the entropy? You can get the temperature at 8 or the entropy at 8. They would both be challenging, but how would you get those? And I wouldn't say they're very accurate, but how would you get that? Let me see if I can interpret it this one. Table A5, which has a table of compressed liquids. That's what got me excited about your answer. You're saying, hey, it's compressed liquid. There's a table of properties, compressed liquid. I know 2 independent intensive properties. In theory, I can get the other ones. So what 2 independent intensive properties for state 8 do I know after a little bit of work? I got H8 pressure at 8. So you got the pressure at 8, enthalpy at 8. Good luck going to that table. May probably have to do a double interpolation, but you can get an estimate, not good to 3 significant figures from my experience, but at least you'll get an estimate of both the T8 and the S8. And if you wanted to, why stop there? V8, U8. I mean, come on. It's just a game of getting properties. All right, that was a hard one. A lot of times we have the particular wording. We have the working fluid going through the condenser, and then we have some other fluid going through the condenser. What's that other fluid? Cooling water. So you should be able to analyze that. I know we've talked about it, did it before. Right? I don't know. Okay, tell me a little bit about state 9 from your experience coming out. What is a good assumption about state 9? Saturated liquid, exactly. Why? It's about ready to go into a pump. For a very good system, designed well, you want to feed the pump saturated liquid. There's no advantage to making it subcooled liquid. And there's a disadvantage for having it two-phase liquid vapor. All right. What about state 11? Is that saturated liquid? It's not saturated liquid at all. But that's a common mistake students will make. I mentioned it before. I emphasize it. Right? So yes, it's compressed liquid typically. What about the temperature at 11? Can you compare it with one of the other temperatures? Let's say, can you compare it to either the temperature at 2, the temperature at 10, the temperature at 12? I mean, compare it to one of those 3 temperatures. Compare it to temperature at 2, because that's the highest temperature coming into the system. Can the temperature 11 going out of the system be higher than the highest temperature coming in? It doesn't make sense for it to do so. You're going to find that temperature 11 needs to be less than, or possibly theoretically it could be equal to T2. Make sense? All right. We already talked about this, but what do we know about the difference between the temperature at 10 and the temperature at 9? They're very close, with temperature 10 being a little higher. Well, I don't have to do a lot of analysis. Is it a pump? Is it a water pump? Well, the temperature is going to be a little bit higher going out of it. Okay? All right. What will students miss when they want to get the heat transfer into the working fluid? They'll say, oh, the rate of heat transfer into the working fluid is H1 minus H11. But they've forgotten this first and second reheat in the energy balance. Don't forget those reheats in the energy balance. And so you'll have, going into this reheat number 1, you have the H of 3 minus H2. That's how much is added. And then if you wanted to correct it to put it on the right per unit mass basis, you would multiply by 1 minus Y1 or Y prime, how your notation there. It's that fraction. Now it's on the per unit mass basis of what went through the first turbine. Likewise, you could do the same to get this Q reheat, second reheat. I'm trying to think of the tripping spots. Somebody says, did I already ask you what is the enthalpy at state 13? Man, see, you're good. If you know what's going on, it doesn't take long. But I'm telling you, I'll ask the question as simple as that, and the students are like, I'm lost. I don't know. How did you get that? Let me ask you, those that called out, how did you get that? The wrong answer is, I just remember what you told me last semester or last lecture, and that's all I'm going to do. Or the other is this is the way I'm going to remember for the rest of my life. I'm going to be able to do a control volume analysis around the device known as the steam trap, and I'll be able to say from an energy balance, no heat in, no work in, no change in kinetic potential, steady state, it's isenthalpic. With confidence, with confidence. Every now and then they'd be like, Professor, look, I'm not certain how to answer these questions on the exam. Do you want me to answer them correctly, Or do you want me to give the answer that you've given in class? It's as if, you know, they're teaching them crap, you know. It's like, but have you ever considered that? Like, I have no idea. Now, I know the answer is this, it's X. But you've been saying it's Y. So I just want to know, what do you want to see on the exam? The correct answer is X. Do you want to see Y? The wrong answer, but that's the answer you've told us it is. Or do you want to see the correct answer X? What do you want on your, anyway? All right, so you can jump around this calculating Y's and Y primes, okay? Did I miss anything that's a little challenging when you solve the problems? Let's press forward. A lot of states, all I have to do again is say, oh, just rub out some of this and say, now tell me this. Tell me H, or tell me S, or tell me P, or tell me T at this state or that state. Or, you know, take away some data and then say, tell me the work of the turbine. Or tell me the heat transfer in the condenser, something like that. See? All right. Is this your friend? Let me give you another copy, just so. Do you want to do me a favor, please? Jessica, you want to start this one on that side? So another page, I loaded up a PDF file about an hour ago to Blackboard Learn, so you can print it off and do it again and again, right? I'll give you another copy today. Should you expect this given a cycle to be able to plot it on a TS diagram, correctly showing where the states are? It's something that I emphasized. Yeah, fair game, right? So there you go. What we're going to do is we're going to come back and we're going to put this cycle on this diagram, okay? But
sir, no matter how many turbines or pumps you have, the backwork ratio is all the summation of pumps over the turbines?
right, make sure it's all on the right per unit mass basis, the same. So the sum of all the pumps divided by the sum of all the turbines.
And if, with each mass flow that's going through that, right?
Yeah, you have to correct back to a common mass flow rate. There's a couple topics. They're covered in the textbook. I'll just be honest right here. Is you get the question all the time, Professor, you've been spending 10, 15 minutes in lecture talking about this. Is it on the final exam? That's all I want to know. Is what you're going to talk about, is it on the final exam or not? And in a way, that's a fair question. But it's, you know, it's like, can I snooze right now? If you want to snooze right now, you can. But quite frankly, most of what's on our final exams isn't relevant to the rest of your life. It's all the little stuff that we try and fill in the gaps that really are relevant, because somebody says, oh, you took a class and blah, blah, blah. Do you know anything about organic Rankine cycles? Nope, never talked about it. Didn't. It may have been in the book, but I never read it. It's in your book, so let me talk about it for a few seconds, but it's not on the final. So basically, what does this word organic mean? What does that organic mean? Anybody taken organic chemistry? One person, very good. That's the first time in a few years. What was the whole point of organic chemistry? Why didn't they say it's inorganic chemistry? Well, they have a whole class in inorganic chemistry. What's the difference between organic chemistry and inorganic? Said the right word. A+. You learned something. That's good. What was the one word I was listening carefully to see? Carbon. Does it have carbon in it? Now, our working fluid is water when we have a steam-based Rankine cycle. Is there any carbon in the water? No. Hold it. I thought it was H2CO. There's a carbon. No, there's no carbon in water. It's kind of obvious. So anyway, if you have a working fluid that has a carbon in it, usually they tend to be a little larger moleculed things, substances, and they have different properties, different boiling points, different whatever PT relationship, pressure temperature relationship. And so if you want to maybe use a low heat source to make electric power, this happens a lot, I don't burn coal. Maybe I burn trash in a garbage disposal site, or I burn some waste product off agricultural use or timbering, lumbering source or something like that. Or maybe I have a low temperature solar collector. I'm not going to get it too high a temperature. You can have very high temperature solar collectors, but a lot of them are just low temperature. Then you may want to pick a fluid that's other than water and run it through the standard Rankine cycle. So it's a little buzzword, organic Rankine cycle. Do you still have a boiler? Yes. Do you still have a turbine? Yes. Do you still have a condenser? Yes. Do you still have a pump? Yes. Only thing you did was change the working fluid. Typically, higher molecular weight organic fluids have carbon. Hence, you're changing to the boiling point, shifting it down so that the boiler temperature doesn't have to be that high before you make vapor.
Is there a reason you want to?
Binary vapor power cycle. What did they do right here? What's that mean? Binary. Just two. So you have a cycle on top of a cycle such that the condenser of one feeds into the boiler, and it's just a heat source. And this would be a good one to have an organic, and this may be water. Maybe you're just trying to get more out of it. All right? And so you're going to have a different fluid that's going to be boiling. You still have a turbine. You still have a condenser. You still have a pump. Just like over here, you still have a turbine. But you have two places you're making work out of the cycle on a binary. Cogeneration. We had this for a homework problem, did we not? So what you may have is you may have some really warm working fluid, but it has a low exergy. I can't get a lot of that converted into work. But what I can do is I can use it to heat a building. Now, you don't see a lot of this in South Texas, but that's because our winters are like half a month long, and our summers are the rest of the year. But up north, anybody ever lived up north, like New York, Minnesota, all that, northern, they have severe winters, and a lot of places don't even have, a lot of homes still don't even have air conditioning, if you can believe it. They have a massive furnace for the 11 and a half months of winter. So anyway, what they can do is they'll have a heat exchanger, and they'll extract some of that heat out of the low quality steam, low exergy steam, and provide it for heating of a building. Especially they'll put it in downtown districts of a big metropolitan area. And they'll have a loop, and that loop supplies from a plant, and it may supply a very little heat in the summer to the buildings, and make electricity, or it may supply a lot of heat while it's making less electricity. But it's a very good combination. We used to in San Antonio, in the downtown area around the Riverwalk and that, through a lot of those hotels, the large multi-story buildings, had a steam line to provide heating for the buildings. But the people found out that they were losing money every year. And so they finally just cut it and let each operator, each building, put in their own boilers and provide the heat for the 2 weeks that they need it in the winter. But guess what we have still in South Texas? We're going to get to the chapter on refrigeration. We still have a loop for chilled water, and that's very popular, and that's a good moneymaker. And there's a plant by the Alamo Dome that makes chilled water and feeds it into the loop, as well as a plant by Commerce, and I know where to get to it, but I don't know the crossroad. But by the Henry B. Gonzalez Center, right across the street. There's a parking garage there, city parking garage, right next to it. So anyway, we're going to cover that when we talk about refrigeration, but there's a chilled water line. All right. I encourage you to do a little exploring. What does some of these Feedwater heaters look like? They're pretty good devices, pretty simple. So here, cold inlet feed water, warmer outlet feed water. You bring in some inlet steam. If it's not already in the two-phase region, it could be slightly superheated. And the first section that it goes through, you're going to be basically, look at that word, de-superheating. You want to impress somebody this weekend? What are you studying? Blah, blah, blah. And then we have D, superheating. There you go. All right, de-superheating zone. And then they have this condensing zone. So basically I would think that right here the fluid is saturated vapor right there. As it's going this direction, comes around. Right there it's saturated liquid. And then they could even have a subcooling zone. I know that in most of our analysis it comes out as saturated liquid, but it would then be slightly subcooled on the outlet for that steam side. But that's what they look like. Hopefully when you get the heat transfer, you say, oh yeah, this makes sense. Shell and tube heat exchangers. You can tell what's in the tube side.
Why would they have a self-cooling zone? Don't you want it to come out as a...
They could have it, but it could be very small or non-existent. There's really no benefit to it, or very little benefit to it. Anybody else? Yeah. Steam traps. Here's some links. You can go and find them. There's the title, Let's Talk About Steam Traps. I don't know how many minutes it is long, but it's a nice little video tutorial, maybe 30, 40 minutes long. They do a pretty good job of showing you, because it's not only holding back the live steam, as they call it, that's the superheated steam, but letting out the saturated liquid. But then a lot of these have to deal with non-condensables, which basically is air, which is oxygen and nitrogen. You do get air into the steam systems, and as an engineer you got to deal with it. Something we don't talk about, but it's very, very practical. Even some float and thermostatic steam trap, they have a nice clear, you can see it operating. They spent some time making some videos. So if you're interested, please go check out a lot of videos. Here's a thermal power plant. There's a full animation of a working power plant. I know it's an animation, but some power utility put it together. I just grabbed one clip showing steam flow through turbines connected to shaft to electric generator. They talk about pulverizing the coal, talk about what's happening in the multi-passes in the boiler. They talk about flue gas and how important it is to not just dump things out to the atmosphere like we used to. There's a lot of engineering to make sure what goes out the stack doesn't harm your neighbor downstream. Aren't you glad if you live near one of these? As well as other aspects of an operating power plant. That's the class. So we're ready to go back and talk about putting that one cycle on a TS diagram, okay? So you come out of the boiler and you come into the first turbine. You got to pick state 1 somewhere. All right, so let's pick it at 8 megapascal, and maybe not 600. Let's pick it at about 400 and 450, right in there, state 1. Why? Because I'm going to expand to an intermediate pressure after the first turbine stage. Where do I really want state 2 to land? Slightly in the dome, slightly in the dome. So if I expand down, maybe I expand down to, hey, let's only go to 2 megapascal. I mean, if I went to 1 megapascal, I'm getting too much liquid. Okay, so let's stop here at 2 megapascals. So we come out from state 1 to state 2, and we're going to divert some down to a feedwater heater. But before we do that, let's take it back and do the reheat right there. So we're going to come down here to state 2. That's a good place for it. It'll be reheated at constant 2 megapascal, but let's stop it at around 350 temperature. Makes it a little different, right? A little more unique. And then let's expand it. This is now state 3. Let's expand it from state 3 through the second turbine down to state 4. And where do you think, what should the pressure at 4 be? Something like 200, 500, either one. Let's go all the way to 200. Now, if you go to 100, wouldn't that be a little too low? All right, so now that we have it there, we're going to take it back for more reheat. And that'll be state 5 before we put it into our last and third turbine stage. All right, so what do you want to reheat to? And let's say we're going to go to 20 kilopascal. So this is where we are going to want state 6 to be. State 6. So how much reheat would I want to put on state 5? Well, let's come up somewhere around there maybe, so that when we come down, 5 to 6. So where did 5 end up? Around 300? Roughly? I'm just throwing out some numbers. All right. Somebody says, oh, I forgot, the isentropic efficiency of the first turbine stage is only 80%. How's it change? You go from 1 to 2s, and then you're going to kick it over, and you're probably going to be 2 out there. Now, guess what? State 2 is now. It's no longer inside the dome, is it? Did you solve a problem where 2 was slightly outside the dome? Did you feel the pain? Double interpolation in the superheated part of the tables, really a painful experience, but I'm glad it's part of your education. I'm glad that you had it, right? All right, so now, same thing, if I had a little, irreversibilities, isentropic efficiency, same thing. It would shift those locations of those states. But now we're going to go into the condenser. And what state comes out of the condenser? 7. And it's saturated liquid at that low pressure. So where is state 7? And we know that after the pump, state 8 is going to be very close to state 7. So a little arrow to indicate where these states are, because we put it through the pump. And then what comes out? State 8. True? And can we plot state 8 on this diagram? Yeah, it's right there, right above it. Right there is state 8. Okay? Now, we put it into our first Feedwater heater. Was that a closed or an open? It was an open. And it took some input from 4. And it took some that was trapped from, I think it was state 13. Can't remember. Should I look back at the diagram? That's correct? Okay. So then it's going to come out saturated liquid. Where this state coming out at state 9, I'm going to pause and walk around. You should be able to put state 9. It's a little more challenging than all other states. But where exactly is state 9 on this TS diagram? All right, so a lot of us had it. It's saturated liquid at that intermediate pressure, the low intermediate pressure, which was the 200 kilopascal. So state 9 comes in right there. Then we put it through another pump. And that's where I got a little ahead of myself, right? Now, where is state 10 after the pump? Sure, it's just like the relationship between 7 and 8, just like 9 and 10. So state 10 is right there. What's the pressure at state 10? You're going to feed a different type of Feedwater heater. What type of Feedwater heater was the first one? Was open. The next one was closed. And so what we're going to do is we're going to have fluid coming from state 2, staying on that, then going down to the trap. And then we're going to come out at state 11. I'm sorry, this is a very complex diagram, right? Overlapped it there, sorry. State 11. All right, so now we know where state 10 is. Where exactly is state 11 and then 12 and then 13? I'm going to walk around. All right, looks like I'm out of time. So what did we say early on about the difference between temperature at 2 versus temperature 11? And a lot of people are putting 11 up here. Is that a higher temperature than at 2? Is that correct? No. Basically, 12 comes out saturated liquid right there. And 11 is going to be typically right there at a different pressure line, but it's slightly lower. Oh, it could be a little lower like that, but typically it's very close, only maybe 5 degrees lower, 10 degrees lower. Because the real heat exchanger, it's not going to get it all. There's always some delta T to drive the heat, okay? So did that help where 11 is? 12, the last one, 13. What is the pressure at 13? Don't bring it all the way down to 20 kilopascal. Bring it only down to 200 kilopascal. And it's an expansion, so maybe I should have written like this. Here is state 12. And then it's a dashed line, increasing entropy because it's very irreversible. And you're going to definitely go into the two-phase region. Some of this steam flashes. State 13 is a mixture. And there you go. Thank you for your attention. We'll see you next time.